First thing we're going to do today is we're going to analyze some titration curves. You guys already know this because of last night's homework, and then we're going to talk about indicators and do some practice. So today, not much new, just some more reiteration of material. Analyzing titration curves. Now when you look at titration curves, you're starting to assume some things, right? You should be thinking about some things when you're looking at this. What I want you to, first off, is tell me what type of curve this is. Strong, strong, or weak, strong? Weak, strong. All right, I'm good with that. This is a weak, strong curve. Now I want to go so far as to figure out what is in the beaker and what is in the burette based on strength and type of substance, acid or base. So we're starting at acidic pH. So based on that and the equivalence point, which is where? Where's the equivalence point, the range? It's above 7, greater than 7. So based on that information, what is in the beaker? Weak acid. And what's in the burette? Strong base. We know that it's a weak acid because with the pH greater than 7, it means the thing that's strong is the base, right? And then how do we know that it's the acid in the beaker and not the base? Yeah, our initial pH is acidic. So before we add any base, that is the pH. Got it? Next one. What are we classifying this type as? Strong, strong. This is actually a student data from a few years back. They did such a great job. I captured their data from the LabQuest. It's pretty nice, isn't it? That was a lot of data collection points they did, though. Every single one of those things was an entry. It was crazy, but it was crazy good because it was beautiful. So, looking at this, we know it's strong, strong. They're both strong, so we don't have to worry about the strength of what's in the beaker and the burette. But what is in the beaker? Tell me if it's acid or base. Yep, acidic start, so we have an acid in the beaker and a base in the burette. And this last one, yeah, it's disgusting. All right. When you look at that, two things I want you to immediately look at, this and then this. Where's my equivalence point? The range? It's less than 7. 7's here. This is 5, 4, 3, 2, 1. So it's less than 7. So we know this is a strong, weak titration. What is in the beaker? Weak base. We know it's a weak base because of the pH being less than 7. The acid has to be the thing that's strong. Because we're starting at a high pH, we know that the base is in the beaker. So that means that in the burette, we have the strong acid. So do you feel pretty comfortable now looking at that kind of thing? Okay. So now what I want to do is talk about indicators. What indicators actually are themselves? They are weak acids and bases. They're usually weak acids, okay? And they themselves have their own K value. So the Ka of this particular indicator is 1 times 10 to the negative 9th. How they work is basically through a Lowry-Bronsted situation. When they get to a particular pH level, they will transfer a proton if they're a weak acid, and if they're a weak base, they'll accept a proton. But either way, a transfer of a proton, and you can see here the proton that is lost and gained is sitting right here. And in that process, they change color. Okay? So when do they change color? Well, it turns out that all of these acid-base indicators, they change color at their pKa. Whatever pH is at that value is when they'll change color. So if we look at this, this is phenolphthalein. Phenolphthalein has a Ka of 1 times 10 to the negative 9th. At what pH, then, does phenolphthalein actually change color? 9. Okay, so this guy turns at a pH of 9. So we want to appropriately choose our indicators to change color when in a titration. When do we want them to change? Yeah, as close to the equivalence point as possible. Okay, so phenolphthalein is best when it's used, and we're going to talk more about this because we use this for all sorts of titrations, and it has to do with the curve. But ideally, we want to choose this color change when we're at the equivalence point. We call the color change of an indicator the end point. The end point is not the same. You're going to hear in your lifetime people interchanging equivalence point and end point when they're not the same thing. End point is when the indicator changes color. Equivalence point is when the titration moles are the same. So ideally, we want the end point and the equivalence point to be the same. Okay? So let's talk about what we see. So do y'all remember we did the Le Chatelier online lab where you were using that bromothiamyl blue and it went from blue to green to yellow and it was going back and forth, right? Bromothiamyl blue has a Ka of 7. So when theoretically does bromothiamyl blue change color? At what pH? Our pH is 7. What happens though from the point it goes from blue to yellow? There's actually a range of pH that this happens. 7, when it was 7, do y'all remember what color it was? Kind of in the middle? It's when it was green. Okay? So in the process from going from yellow to blue or blue to yellow, in the middle of that range is green. So what is the range that we see color change? Because we don't see exactly at a certain pH. You see, the way your eyes work, you kind of see the color transform, right? So that is a range. And it has to do with the fact that the human eye, 1/10 of the color has to change before we see a change. So this is really cool. I just wanted to show you the calculation. You don't have to know this. I'm going to show you for those of you who are interested. Remember, these are weak acids, these indicators. So they have a Lori-Bronsted thing. They have an acid and a conjugate base. So in order to see color change, at least 1/10 has to change. So from this direction, if we have 1/10 of the indicator turn into conjugate base, this would be the ratio, right? So this is where they get our low end of 6, just by doing Henderson-Hasselbalch. The pH is when it changes, but because of the whole 10th thing with our eyeballs, this is the low end pH. Now, if we were to look the other way, where we had this from the indicator, 1/10 of it turned back into the acid, the conjugate base turned into acid, we'd end up calculating with Henderson-Hasselbalch and we get a pH of 8. My point of all this is that the indicator, what we see, is not only the pKa of 7, we have a range of our eyeball of plus or minus 1 pH unit. Okay? So phenolphthalein, it had 1 times 10 to the negative, what was it, 9? Yeah, so we know its pKa is 9, but what's its range then? 8 to 10. All right? So our indicator's range is the pKa plus or minus 1. And I just thought it was interesting for you to see the whole plus or minus 1 thing, where it came from. So these are some different indicators in their different ranges. We're usually within 2 pH units. The ones that look shorter are mainly because it gets colorless. So it doesn't have a color. But all right, so now let's talk about choosing an indicator. Phenolphthalein is a universal indicator, and it's cheap, super soluble, very easy to deal with, very, very common. You guys did in pre-AP a phenolphthalein titration, right? But you did strong, strong. So the question is, and this is something kind of people will question me about, teachers even, will be like, well, when I talk about this, they're like, well, phenolphthalein is used all the time, and we do it with strong, so the equivalence point is 7. That's out of the range of 8 to 10. Well, that's true, but it has to do with the shape of the curve. So this first curve right here is a strong titration. We see that the equivalence point is at 7, right? So the question is, what do we want to use? Can we use phenolphthalein? Can we use methyl red? They're both really far from the equivalence point. What matters has to do with the amount of base you add. If you look here, this is at like 100 mils, right? Do you see how that 100 mils, because the rise is so sharp, one drop difference from here, like is there, do you think, even a drop difference between here to here? This rise happens so fast within one drop that because this volume, the start of the color change, is really the same volume added as that, we can go ahead and use that indicator. Same thing, could we use methyl red? Absolutely. Methyl red's volume, I think methyl red's even better actually than phenolphthalein. Methyl red, looking at this curve, works as well. Okay? However, when we come to here, which one can't we use? Yeah, we don't want to use methyl red for this particular one. This is a strong base weak acid titration. Fantastic for phenolphthalein. Our equivalence point actually falls within the range. But here, look at this volume. The closest we could get to the equivalence point and see a color change is right here. How many mils is that of a difference? A lot. That's 50, right? So that would be 45. So it could be like 2 to 3 mils difference. That's a big difference. So we cannot use methyl red. Does that make sense? Okay. So there will be questions on the AP asking you what indicator to choose, just like in this problem. They'll give you the Ks, and so you'll be able to pick one that's appropriate for where your equivalence point is. Okay, let's see how y'all do. First period, the struggle was real on this one. But I'm going to give you a little preemptive discussion here that I didn't give the last period, so I think that was my fault. Up until this point, when the very first exposure you had to titrations was to figure out the concentration of an acid, right? So you went to the back, you made this curve, and what on the curve did you go to? What was important about your curve when you did your calculations? What did you look at on the curve? The sharp rise. You were looking for that equivalence point, right? Okay. That's why we do titrations, to find the equivalence point in order to find something else, something out about something we don't know. So it's always find the moles of known, moles of unknown, and then what we're looking for. Remember that? Yes? No? Okay. What we did yesterday or the day before was just construct a curve using both knowns. We knew both the concentrations, we knew everything, and we just made a curve from it. So that's not normally what we do with titration curves. This is normally what we do with titration curves. So we got to go back a little bit and make sure we understand the point of titrations. A 30 ml sample of a weak monoprotic acid, what's monoprotic? 1 hydrogen, was titrated with a standardized solution. Does anyone know what standardized means? Anybody? Standardized means the concentration has been verified through some sort of process. It also means we know this concentration. This is our known concentration. So, titrated with a standardized solution of sodium hydroxide. A pH meter was used to measure the pH after each increment of sodium hydroxide was added, and the curve above was constructed. The first question, explain how this curve could be used to determine the molarity of the acid. So what is the first thing you would get from that curve? What about the equivalence point? How does that help you find the molarity of the acid? You want to find the mils at the equivalence point. Find moles at the equivalence point. Noah, what is knowing the pH? What's the only thing knowing the pH does? No, but what does the pH at the equivalence point tell you? It does tell you something. What did we assume? We figured out whether or not the acid or base was strong or weak, right? That's all we can get from it. There's nothing we can get from pH that's useful, other than, we kind of know now that this is a strong base, weak acid situation. That's it. But finding the moles at the equivalence point is the moles of NaOH, right? So what would be my next step after that? Find the moles of the known. So we can take the molarity of NaOH times the liters from here, from the equivalence point, and what does that give us? Moles of NaOH. Who cares? Why do we care about that? Yeah, that is the same as the moles of the acid. So the moles of, because we're at the equivalence point, the moles of NaOH is equal to the moles, I'm just going to call it HX because we don't know what monoprotic acid it is. The moles of HX, because we're at, like I said, the equivalence point. Okay, we're getting there. I got to get to concentration of the acid. That's my goal. So what do I need to do? What volume do I divide by? I just want the original acid's concentration. So what do I divide by? The 30 mils, because that's how much we put into the little thing. So that's 0.03 liters. And that'll give you the concentration of your H+, and since it's monoprotic, it is also the concentration of your acid. Okay? Does everyone understand that? That's what we did very first flipping week of school this year. But you didn't have all this other stuff in your head, so that was easy, and now you're all confused. Don't be confused. It's still easy. All right. Part B then, another question. Explain how this curve could be used to determine the K of the weak acid. Midpoint, exactly. Midpoint, or half equivalence point. So how do I find that? What do I do? Take half of the mils to the equivalence point, right? So in this particular case, our equivalence point is about 24-ish, right? So half of that is about what? Go to 12 mils. And figure out what the pH is at that point. Bink, bink. So that's approximately a pH of 5. What is true at the midpoint? Yes, at the midpoint, pH equals pKa. And that's going to be an important part of your explanation when people say, well, why? Because you say at the midpoint or at the equivalence point, pH is equal to pKa. You don't need to go into further than that. If you just say that, you're fine. So if we know the pH of the equivalent point is 5, what is the Ka of this acid? 1 times 10 to the negative fifth. That's approximately what it is. So the question didn't ask to find it. The question asked to explain how to do it. But by finding it, you're explaining how you do it. Okay? So 10 to the negative 5 will give you your Ka. Okay, part C. If you were to repeat the titration using an indicator in the acid to signal the endpoint, which should be equivalence point, but sure, which of the following would you select? Cressel red. He didn't fall for it. I get worried. A lot of students see this, and they see that one happens to match their answer from the last part, but this is the midpoint, right? This is here. Do we care? Do we want the indicator to change color there? No, we want it to change color in the middle of the sharp rise, which looks to be about a pH of 8. So indicators change color when? When do indicators change color? At what? At their own pKa, right? So a Ka of 1 times 10 to the negative 8th, its pKa is equal to then 8. That's closest to where? To the equivalence point. Okay? All right, the last little bit of this problem. Sketch a titration curve. We're just going to put it on top of the graph. If the weak monoprotic acid were replaced by a strong acid, such as HCl, how would it look different? Start lower. It's now strong, strong. What's the most important part about strong, strong? Equivalence. And that's what I would do. The very first thing I would do is mark where 7 is. 7 is here. Since that's 7, that would need to be the center of my sharp rise. So my sharp rise would need to be about that long for 7 to be the center. And then they're not specifically, they say sketch, so they're not specifically looking for like a number, like a certain value. Then I would drop it down from there. Again, you want 7 to be the middle of that sharp rise. Okay, I really like that problem. I think it's a really good problem. Okay, now we're going to do one more oldie but goodie that encompasses not titration stuff, but it's just a review from the other parts of the unit and kind of indicative of what's the big picture, everything you need to be able to do for tomorrow's quiz, for the group quiz, for the test, and for the AP. All right, in water, hydrozoic acid, HN3, is a weak acid that has an equilibrium constant, Ka, equal to 2.8 times 10 to the negative 5th at 25 degrees Celsius. A 0.3 liter, apparently back in the 80s, they used the British spelling for liter, sample of a 0.05 molar solution of acid is prepared. So you have a 0.05 molar weak acid. You got about 1/3 of a liter of it. A, write the expression for the equilibrium constant. And I always look at what's next, and then I have to calculate the pH of that. So let's classify this. We're finding the pH of what? A weak acid. That's just a normal rice table, right? Well, I like to have my expression written after I write the reaction, right? So I'm going to go ahead and just kind of start my rice table for part B first, just to get my equation, and then I'll go back and write my expression. So I'm doing a weak acid of HN3 plus water. I'm putting it in a rice table to find the pH. The acid is a proton donor, so what are my two products? N3 minus plus H3O plus. All right, so now I can write my K expression. So Ka is equal to N3 minus times H3O plus divided by HN3. Okay, so do I have an initial concentration to put in my table to find pH for part B? What is it? 0.05. Why don't I multiply 0.05 times 0.3? Isn't that what I've been doing for the past few days? Yeah, that's to find the moles in an invasion. That's not what we're doing. We're just finding the pH of this solution. Doesn't matter how much we have. It's based on the concentration. So this is 0, 0, minus x, plus x, plus x, 0.05 minus x, x, and x. I can drop this x. Because I already have my Ka down there, I don't need to rewrite it. 2.8 times 10 to the negative 5th is equal to x squared over 0.05. X then, which is equal to my H3O plus concentration, is what? Anybody? 0.00118 moles per liter. So then my pH, let's see, we have 2 sig figs in the concentration and 2 sig figs in the K, so give me 2 decimal places. 2.93. Okay, so that's part B. Part C. To 0.15 liter of the solution, so we took half of our solution. We added 0.80 grams of sodium azide, which is a salt. The salt dissolves completely. Calculate the pH of the resulting solution at 25 degrees Celsius. The volume of the solution remains unchanged. So we add this to 0.150 concentration, molarity, of our already existing HN3. Can anyone tell what we did when we put that salt into that water? What did we, not water, into that acid, what did we create? Do y'all see that's a buffer? This is technically adding N3 minus, right? So we have 2 conjugates there, a pair of conjugates. So, buffer solutions, how do we find pH? Harrison, close. Henderson. Henderson, Hasselbalch. My co-teacher from like many years ago, he used to call it the Heineken-Hasselhoff. It was like beer to Baywatch approach to chemistry. Henderson Hasselbalch. Now I'm confused. Henderson Hasselbalch. So we need the concentration of the acid and the ion, right, to do that? Well, we've got the concentration of the acid. Oh, that was liters. That's just me being dumb. 0.050 molar HN3 might be. So we have the concentration still of the acid. We just need to find the concentration of the salt. When they say assume the volume remains unchanged, what they're saying is when you put that little amount of salt in there, your solution is still 0.15 liters. So you're allowed to then divide this moles once we get it by 0.15. So let's find the molar mass of this sucker. We have to do the molar mass of the whole thing, not just the N3 minus, because that's what we're weighing on the scale. Okay? So for every 1 mole of this, how many grams do we have? And it's 0.8 grams. I am not having a good day. 0.80 grams. How much, Chloe? 65.8 or O? 0.02 grams. All right, and then that's moles. So are y'all cool with me just dividing by the liters down here of 0.150? That's going to give me moles per liter of this guy, because for every 1 sodium azide, there's 1 azide ion. All right, what is the molarity here? Can I get a second? All right, sounds good. So now we have, this is of the N3 minus. So now we have everything we need for Henderson-Hasselbalch. pH equals to the negative log of the pKa we had above of 2.8 times, not the pKa, the Ka, taking the pKa, plus the log, concentration of the ion, 0.082, over the concentration of the acid, 0.050. So what is our pH? .77. I think that's what I remember from last period. Right? Are we good with part C now? So we added some salt, which made a buffer. We found our concentrations of both and solved with Henderson-Hasselbalch. So our last thing we have to do is part D. Part D. To the remaining 0.15 liters of the original, so we messed with half of it in part C, now they're going to mess with the other half in part D. they added 0.075 liters of 0.1 molar sodium hydroxide. Calculate the OH minus for the resulting solution. What did we just do to our poor weak acid? We invaded it. So our invasion equation, OH minus plus HN3, it's going to go to completion. The war will make N3 minus plus water. All right, so now what do we need to put in this table? Moles. So our moles of base, 0.1 times 0.075, that's 0.0075, right? Now remember, we're not adding it to C, we're adding it to the original acid from the top, which was 0.05 molar, right? 0.05 times 0.15 is, it's also 0.0075, and we have 0 of the azide at this point. So we're going to lose 0.0075, we're going to lose 0.0075, and we're going to gain 0.0075. So when we're done with the invasion, we have 0, 0, and 0.0075 moles of N3 minus left hanging out after the invasion. That's all that's remaining. So what kind of problem is this now? Salt hydrolysis. So we're going to utilize that. Now they're asking for the OH concentration, which is great because we don't then have to go find pH. So we'll stop a little short of that. But what do we need for sure, though, in order to find that concentration? In a rice table, we need molarity, not moles. So our total volumes, we had 0.075 plus 0.15. So go ahead and figure that out while I turn off my phone. Everyone at home gets to hear my ringtone. That's awesome. Okay. Go ahead and tell me what the total volume is. 0.225. So this is 0.225. So my concentration of N3 minus is 3 repeating. Okay, so now we have our concentration. Now we can do our salt hydrolysis problem by taking our ion, putting it in a rice table, adding it to water, making HN3 plus OH minus. Well, that's good. We're going to get that out. That's what they want, is the OH concentration. So all we have to do is find X, theoretically. So this is 0.033300 minus X, plus X, and plus X. 0.0333 minus X, trumpet, X, and X. But because it's hydrolysis, we need the Kb of the conjugate base, and they only give us the Ka of the silly acid. Wait, what am I doing? It would be products, Demo. Products over reactant. So they only give us the Ka of the acid. We need Kb of the conjugate base. So we're going to take 1 times 10 to the negative 14th divided by the given Ka. That's equal to X squared over 0.0333. The X then, which is equal to what we're looking for, OH minus, is, give me 2 sig figs, please. Yeah. 3.4 times 10 to the negative 6 moles per liter. Is everyone happy with that number? Okay, so that, my friends, is what they're looking for. They're not looking for the pH, so we don't have to go any further. And that is the unit. So you have now officially over a week to get this all in your heads.